Hi guys, so today we are going to talk about something called the app monitoring, which is more or less become as very essential for all the apps which are hosted over the clouds these days, because all the business logic currently resides on the cloud. One of the primary problems that we figured out for a lot of our clients was once they go live, they didn't realize what is actually happening in the applications that they have deployed over the clouds, or over the time as they scale, they get more consumers, they don't know how much resources are they supposed to allocate. They generally have the problem of either the under allocation of the resource or over allocation of the resource. By resources I mean the CPU allocated to the cloud server, the RAM that has been allocated, because at the end of the day all the resources comes at a price. So we don't want the under allocation of the resources, which will lead to the failure of the incoming request. Neither do we want the over allocation of request, expecting a higher traffic at some point of the day, just to make sure all our requests are processed successfully. So for this we needed a tool. We realized the need of a tool that can help us not just at the real-time monitoring of the state of the application that we have deployed, and even getting the historical data, because sometimes the things go wrong, and as a developer I will have a tendency to restart the server to make sure everything comes up back again and all the apps are working, or the website or the dashboards are working. But we don't really ever actually realize what was the problem that was there. So we internally started, when we figured out this is a problem that we experience across the teams within our company, and this is a common problem that has been experienced by a lot of people who are into the cloud application development. So we went ahead and developed something in-house. So we call it Trace, and that's something we ship all our apps with. Now I say application monitoring, it's not restricted to the physical resources monitoring of the server. We get down to the API level and we realize which is the API that is acting as a bottleneck into our entire application. When I say bottleneck, it means the API which is not performing as per our expectations. Like imagine we expect a response to be sent back to the client within 50 milliseconds, but under certain conditions which might be a higher throughput in terms of other API requests, that's leading, or a load over the database server, leading to the queuing of the request, which ultimately leads to a higher response time. So let's start with what all we cover in the application monitoring, which are bare minimum essentials. So first of all, we have a system level monitoring in the application monitoring that helps us monitor the physical resources in terms of CPU usage and the memory, incoming or outgoing traffic, context switches and interrupts. So I'll tell you a practical example. The problem that we faced internally was one of our servers that was not a production server. Of course it was a development server, but it got it got hacked and somebody was using it to mine the cryptocurrency. So what the person was doing was, it was using the CPU resources on our server, and after 1 hour, whatever the currency that has been mined, he was shipping it out to his server. Now this looked for us like a normal day problem, since the server was still in the development. So we was not expecting a very high throughput, but still we realized that some of our APIs are responding quite slowly. So when we logged into this dashboard using the application monitoring that as a tool that we have, so we realized a spike in the outgoing network traffic every 1 hour. So then we checked back and see the throughput of the APIs, and we realized there was no incoming request spiking after every 1 hour. So there was something suspicious going on. Then we connected the other graphs and we realized that there was a very high context switch and the interrupt rate, which basically defines if there is a IO bound job, and for that time the CPU preempts that process from the processing and give the CPU time to another process. So this is called a context switch, and when the process is done with the IO bound job, let's say by accessing the disk, it interrupts back the CPU that I am ready, now I want the CPU. So this was one of the reasons where the system monitoring helps us realize figure out, or let's say helped us to mitigate the some attack over the when it was using the cryptocurrency. Then other thing that we often realize with let's say we are running a MongoDB server, so we often realize that as a, let's say, not somebody who's not into enterprise grade development solution, all the people, they have this very common tendency of not having the log rotation in place. So what that leads to is, if a server on which a MongoDB has been set up has been live for more than a year or so, with a decent number of incoming requests, so the log keeps on increasing, the log file size keeps on increasing. What that leads to is, after a certain point of time, every time a query is made into the MongoDB, update or a fetch query, any statement executed against the MongoDB, it has to be logged into the log file. And we realized on one of our servers, when we were monitoring the disk usage, that the log file was consuming around 16 GB. So every time a new operation has been triggered over the MongoDB server, that it used to read that entire file, leading to very high CPU consumption. It was like 200% CPU consumption on a quad-core processor. So this is one of the components that we have. Apart from it, there are a lot of technical things which might not make sense on a normal day, but when you are stuck into a problem and you want to troubleshoot to the trouble point, then there helps us connect. So some of those things include, of course, there is a concept of a load average, which specifies the 1nm, 5nm, the 15nm, which basically means what has been the load in the last 1 minute, what has been the load in the last 5 minutes, and what has been the load last 15 minutes on my cloud server. So what that basically means is, let's say I get a value of 1.5. So still CPU is a state machine. So see, when I said 20% CPU usage, CPU is a state machine. So it's not possible that 20% of CPU is executing one process and the 80% of CPU is executing another process. What that basically means is, when I collected the last 10 samples of the workload from the CPU, 20% of those samples were given to this process. Basically, at a time, CPU can either execute a process or not execute the process. So it goes into a round robin method to give the CPU computation power to each of the processes who wants to have it. So when a load M is above 1, what that basically means is, when I took the last 10 samples, or let's say last 100 samples, so it was a task was already available to be done in those 10 samples, and 5 more tasks are queued for the next samples. So basically, when I say sample, it means a time frame. So load of 1.5 means it was occupied in all the last samples that I took, all the 100 samples, and even in the next 50 samples it is supposed to be occupied. So that's how we measure the idle or the idle or the busy percentage of the CPU. So it helps us make me figure out what has been the load distribution of my servers. What I'll tell you a practical usage of it is for the load testing. We also do the penetration testing as well as the stress test over our product. So let's say, imagine you have a Uber clone. So you want to figure out how many concurrent users it can support. When I say concurrent users, it means concurrent users making a booking request. Or let's say I have a WhatsApp clone, then I want to figure out what is the number of users who can concurrently message. Or let's say I have a predefined requirement that I want to figure out how many resources do we need to have a throughput of 20,000 messages per second. So it works both ways. So we also do sort of a consultancy for our clients. Unlike most common tendencies, people go after assumptions that, okay, a client comes up with a requirement that, okay, I want 20,000 concurrent requests in a WhatsApp clone. Then they say, okay, fine, 8 GB server is required, and then it needs to be quite code. Now, there's no proof involved. So what we do is, we have a proper automated scripts running, and we measure the physical resources involved, and then we can give you exact reason that we need, okay, if it has been distributed across the entire cloud or the data center, then we need a 2 GB server just to handle the backend, API backend, which might be API, Python, Go, Alexa, any language. We need a 4 GB server to run a database. So we monitor it not just at the physical resource level, also at the process level, and then we sort of benchmark the resources required for each of the processes. now this, apart from this, the few other things that we monitor at the system level monitoring is of course the memory usage. So even the memory usage, sometimes we have quite a decent amount of RAM involved, but it has been allocated to the cache processes, buffers, slabs, swap cache, page tables, virtual machines, inactive. So there are various components into which the memory is divided, and then at some point of time there is a limit to the vertical scaling that we can go. So we cannot get a server which generally has more than 128 GB of RAM. Generally you get a cloud server of 4 GB of RAM. So then we want to optimize the physical resource that we have unless we move into horizontal clustering. So that's one of the things we monitor, not just the RAM usage at the broad level of what is the RAM currently used, what is the RAM that has been historically used, or now what is the RAM that is available. Apart from it, even further subcategorization and at what is the exact pain point that is leading to the higher RAM usage, because we have realized that let's say for a Node.js server, again using this tool, we realized that if the heap memory is not configured properly, that was leading to high number of let's say unnecessary open file descriptors. Again, the one more thing that we measure is the open file descriptors. So it was leading to high number of open file descriptors being opened. So these are the few things that we cover. That should be good enough.